In math, symmetry is an action performed on a shape, leaving it completely unchanged. Think of an equilateral triangle sharply snapping into a new orientation. If you track every possible rotation and reflection that brings this triangle back to its starting footprint, you will count exactly 6 states. It is a clean, discrete set of mathematical operations. But out in the physical world, reality often moves in fluid, continuous motions. Consider a frisbee gliding through the air. As it flies, it spins continuously. You can rotate it by 1 degree, or 1/10 of a degree, or any microscopic fraction, and it will look identical. It possesses an infinite number of symmetries. Back in the late 19th century, mathematicians struggled to calculate these systems. The methods used to study discrete groups, like our triangle, could not account for operations that were uncountably infinite. Because the physical universe moves in fluid, continuous motions, rather than rigid, separate steps, mapping reality required a new way to handle infinity. In the 1870s, mathematician Marius Sophus Lie realized he could map continuous transformations by using the language of geometry. He took a single operation, like rotating a spinning object by one specific tiny angle, and plotted it as a single coordinate point on a graph. When you plot a point for every possible fraction of a rotation, those infinite dots fuse into a solid line. What emerges is a smooth, solid shape. In mathematics, this surface is called a manifold, and this specific circular manifold represents the rotation group known as SO2. Complex physical actions create even more intricate geometries. The group of all 3-dimensional rotations of a sphere, for example, forms a 3-dimensional manifold that lives inside a 9-dimensional space. By converting infinite physical actions into solid geometric manifolds, mathematicians could finally visualize the math. However, calculating motion across these massive curved shapes remained difficult. To solve this, Lie relied on a property of all smooth manifolds. If you zoom in close enough, the curve disappears. When a spinning object rotates by less than 1 degree, any given point on its rim follows a path that is practically linear. Mathematicians can approximate the complex curve by drawing a straight tangent line that touches it at just 1 point. This line is known as the Lie algebra. This diagram shows mathematical calculations and geometric shapes where circles intersect with linear paths. Using this relationship, mathematicians can avoid doing complex calculus on a curve and use simple linear algebra instead. The Lie algebra provides a localized, straight-line window. It allows us to calculate the properties of impossibly complex global shapes using the math of a straight line. If you pull back from the abstract geometry and look at the macroscopic universe, the fundamental forces follow these same continuous symmetries. Consider the gravitational pull of the sun. That pull depends strictly on distance, regardless of the Earth's orientation. It maintains perfect 3-dimensional spatial symmetry. In mathematical terms, gravity's behavior is defined by the Lie group SO3. In 1918, the mathematician Emmy Noether established a direct link between these abstract symmetries and the laws of physics. She proved that for every continuous symmetry in a physical system, there is a corresponding law of conservation. For instance, the fact that the laws of physics are the same today as they are tomorrow, a symmetry called time translation, dictates that the universe's energy must be conserved. By turning infinite curves into solvable tangent lines, Lie provided the framework used to define gravity, electromagnetism, and the nuclear forces as measurable geometric symmetries.